Welcome to another read along with Dr. Powell in the book Discrete Perspectives on Mathematics. We're now looking at section 1.2. Okay, so the parts of a function. We're going to split the action of a function of merging and relabeling into parts and kind of looking at it in particular. One notion which we will be using at times in this text is something known as a commutative diagram. Let's start off with what this means. See this function f and a, b. This means a is the domain, b is the codomain. It's kind of like you're taking something in this set and you're like projecting it or setting it over here to something over here. You can notate this with an arrow, the function like an arrow here where you put f above the arrows. So going from a to b, this just means that a is the domain, b is the codomain. And in particular, you can look at something like this. Maybe you could have two functions together. So maybe a function f goes from this set to that set, function g goes from that set to that set. And if you're familiar with compositions, like g of f, you could make an arrow that goes like this. G of f goes from A to C, and it goes to B, G. Now, this right here actually is an example of a commutative diagram. Why? Because, well, if you take any function arrow path from A to C, like this way or this way, you should get the same result because both mean the same thing. I mean, this arrow means you do that and that. That's what it means for a diagram to be commutative. An arrow diagram is meaning you can cross through arrows in any way you like, either this way or that way, and you get the same thing. That's what commute means in this particular sense. So here's a commutative diagram actually, and I give you some definitions for these functions. So the function f means you double a number, the function g means you multiply a number by 15. J means you triple a number, and k means multiply the number by 10. Notice that if you follow this path or that path, in the end, you're going to be doing the same thing. You're going to be multiplying by 30 either way as you go from here, from beginning to end. So that's kind of an example of a commutative diagram. Let's look at the next subsection, parts of a function's action. Okay, so a function, all right, we can think of first in the process of merging, relabeling. Let's just first merge. So we stay within the same domain set, just kind of merge different domain elements together, and then we'll relabel to the codomain set. So stay in domain first, then let's move to the codomain set. So for instance, let's look at this right here. This function goes from A, B, C, D, E to 1, 2, 3, 4. And we'll take, instead of having a table, let's use a fiberbox diagram for the definition of the function, meaning that A goes to 2, B goes to 2, C goes to 2, D goes to 3, E goes to 3. All right. We can take this function in two parts. Let's first stay in the domain, which is A, B, C, D, E. Okay, what happens there? Well, looks like A, B, and C are merging together. So let's merge them together to something in the domain. We basically just pick any one of these. It could have been B or C, but just pick A, that's fine. And then over here, D, E, notice they're going to the same place. So let's merge them to E. So this would be like a merge function. You're staying within the domain set and you just merged. And then you can relabel to the codomain then. And this is the relabeling. So A goes to 2, E goes to 3. Notice that the relabeling function is injective. And the merge function right here is, in this particular case, if we choose, if we choose the image of the merging to actually be the codomain, in the sense that it's surjective. So we're going to do that as we split this function up. So we're going to split it up into a surjective function where we're actually just hitting the image that we just restrict down the codomain, so it is surjective, followed by an injective function. And notice when we make it injective, then we can actually spread out to the whole codomain that we wanted to in the end, which was 1, 2, 3, 4. So, but we can take any function at all and split it into a surjective function first, followed by an injective function, and we can do it with anything, at any function at all. So for instance, and you could, this is just another example where you could have not just used A, you could use B or something like that. Okay, and there's different ways of notating what's going on. Okay, so let's take a look at the next little subsection, little boxes inside of big ones. Okay, this is another way of actually describing commutative diagrams a little bit. Now don't get lost, the notation here is a lot simpler than it seems. I might look at it and say, oh, what's that, right? Okay, so this guy right here, okay, actually, if we jump back to, okay, so I'm going to jump back right here to this subsection, which is the last subsection of section 1.1. If we look at this, there was a notation introduced. This is akin to this notation right here of unioning. In fact, it is kind of like a union if you think about everything coming from this guy being completely disjoint from anything coming from here. Even if they have the same label, we just kind of like don't merge them together. We just kind of keep everything distinct. Like here, notice how if we have a set 1, 2, 3 and a set 2, 3, 4. So we're going to think of this, notice there's an overlap with 2, 3, but we're going to think of this 2 as being like a 2A because it came from A. This 3 as being like a 3A. And so really notice how they're all distinct here. This is called a disjoint union. A disjoint union of two sets where you think of everything in this set as never having the same label as things having this set. Then you just take a union. That's basically what that means. So we're going to use that this symbol here in what we're going to be talking about here in this section. So let's go back here to where we were. Little boxes inside of big ones. Okay, so if we're taking a look at this symbol, this is a disjoint union symbol. What is A1, A2, A3, and so forth? Those are just subsets. Okay, so this is just a general definition which you're going to be using, but what we're going to be doing is we're going to be doing this with fibers. So we say that a set S is partitioned by subsets if the disjoint union of those subsets is actually the set S itself. Meaning that these guys don't overlap anyway, okay? Because if they did overlap, this could never be S, really. These guys right here, so this notation also sometimes just means that these guys don't overlap. It's just completely disjoint, and we're taking a union. So you can really think of this symbol as just being straight old union here. But with the caveat that A1 through AN, they're disjoint. They don't share any elements. They have no overlaps at all. And if we can do that with a set S, we've created a partition. The partition, so we've kind of divided it into distinct disjoint pieces or boxes or subsets. That's really all this notation in Jazz is talking about. You just take a set and you split it up into disjoint boxes. That's it. Okay. There's different ways of notating that. That's pretty much what it is. Notice that these fiber box diagrams represent partitions, especially when we're thinking of a surjective function. We have partitioned the domain up into distinct parts, right? And if we put them all together, we get the full domain. That is a partition. So this is like a fiber partition of the domain of the function. We have some kind of fun notation for this. the fiber over 3. So notice that we're just looking at a merge function right now, where we're just kind of, we stick with, we don't take labels outside the domain, we kind of stay in the domain. Notice that if I have 3, and I'm putting this bar over this, kind of representing a chunk. Now, the color is not important here. It's just, you could just draw a line over it, but I thought a red bar looked kind of fun. And also, if we're talking about different functions, it might be nice to use different colors to represent the chunking that happens with different functions. So what does 3 bar mean in this case? It just simply means the chunk that, or the fiber, or the chunk of this initial merge function that contains 3 in it. Now 3 is also in the output of this merge function because we're staying in the domain, because they're just merging right here together. But essentially you take this chunk 3, 4, 5, and if you say 3 bar is going to be equal to the whole chunk. So it's a way of notating the chunk that 3 is in of this particular function that's merging. Likewise, 4 bar would give you the same thing as, you can see that right here, 4 bar would give you the same thing, 5 bar would give you the same thing, 3 bar as well. It's notation. We're going to be using this a little bit as we move along here in different parts in this book. Okay, there's another notation that we can use for a particular function. We could say that, notice 3, and then we could say congruent to 4 via this function, where we have 3 lines, not just an equal sign, but it's 3 lines. What does that mean for this particular function? That means that 3 and 4 are in the same fiber of this function, the same fiber chunk of this particular partition that's defined by this function. An equivalence relation is nothing more than this, basically the relationship of the symbol of saying whether 2 things are in the same part of a partition of a set. And a partition of a set, if I give you a partition, I've actually given you a fiber box diagram, so I've actually given you a merge function. So really there's a function involved with every single partition, meaning there's a function involved with every single equivalence relation or chunking. If you like take a set of things and you say, okay, all these things over here, we're going to say are equal. These other things over here are equal. These other things here are equal, but they're not really equal, but we're saying they're the same in some sense. And so since we're saying the same in some sense, we say congruent. And that would be an equivalence relation. So for instance, okay. Wow, what's going on here with this? This is a fiberbox diagram. Look, it has a fiberbox diagram within a fiberbox diagram. Notice, but you don't have labels here. But if you thought of this as a merge function in here, you could put a 3 and a 5 here just fine. If you just thought of this as merge. So it really is a fiberbox diagrams inside of a fiberbox. It's kind of like you have like one function inside of another, because you've kind of partitioned one. You've partitioned each chunk up again. And so we kind of have 2 functions, one after another, if you will. But not only that, you could also think about following. Okay, so we have this function f, okay, from D to C, okay, from above. And notice we have this refined partition where we have chunks inside of each chunk exactly. Maybe we could pull that apart. See this 3, 4, 5, 1, 6, 2, 7, 8. Let's just pull it apart, string them out. And then we have this function. Okay, let's think of what's happening here. Let's just have a, let's define a function here and see kind of what's happening. But let's let this function be actually what's happening here. Let's let 3, 4 go to 3 and 5 go to 3. Hey, let's see. Oh, 3, 4 is going to 3 and 5 is not going to 3 quite yet. Okay, so maybe this is just a merge function so far. Okay, so this is just a merge function. 1, 6 is going to 6, 2 is going to 2, 7 is going to 8. Okay, so we're just merging. So G is merging. So G is like the function that merges before we complete off and actually maybe do what F is doing. Okay. All right, so let's suppose we have this merge function, and this merge function represents a refined partition or kind of another partition of the same initial domain set. Notice this domain, so we're having like this merge function here. This merge function represents a partition, and this the function f, okay, which we were doing before right here, represents a partition, and the function g actually gives a subpartition of the function of the partition that was given for f. So that means that f and g, they both chunk up the domain, and so they both have an equivalence relation. So, so we're going to use this notation for the equivalence relation to see if two things are in the same chunk with the function g. We read this mod g. So 3 is equivalent to 4 mod g. Yes, right there. 3 is also equivalent to 4 mod f. 4 is not equivalent to 5 mod g. Notice that these both didn't go to 3. I kind of caught myself in that, right? So, but this is distinct here in the partition itself, right? 3, 4 is a different chunk than 5. They're not in the same chunk. However, in F, they are, right? Yeah, so we kind of have that sense here with that. And so we can kind of think about what this particular symbol means with the equivalence relation here. We could have used the other notation with bars here, but we chose in this sense to use mod f and mod g. Okay, so let's kind of look at this a little bit here and kind of build things up with what's happening. I'm just kind of scroll down here for a little bit, and let's take a look at another function. All right, let's kind of think in this sense. Let's suppose that we have a function that goes from A to C. So 1, 2 is kind of like a fiber for an element here. They merge together. 3, 4 merges, 5, 6 merges, 7, 8 merges to something. All right, and that's this set here. Then we have another function here that takes 1 and 3 and merges to 1, and 5 and 7 and merges it to 5. Okay, in that particular sense. But we could have done this, right? We could have said, okay, 1, 2, 3, 4, and we blocked them in a red block, and 5, 6, and 7, 8, and blocked them in a red block. And we're kind of thinking about this. First, we have a function that goes somewhere, or a function that has these chunks, the green chunks. And then we have a further chunking process. It's kind of like we have one function followed by another function. So we chunk it, and then we further at bigger chunks, we have one function following another function. And we can do this simply just with boxes inside of boxes. So let's suppose, for instance, that we have another set. Okay, another setup here. Let's take a function that goes from A to B, and let's suppose that it's given by these fibers, this fiber box diagram here. Okay, so F is going to B. All right, and we're going to use the same setup here with A going to D via C from this diagram. So A to C to D here. So notice, so this diagram kind of follows the same idea. So A to C to D, and now we're introducing another idea. A goes to B, and we have a question. What happens? Can we complete this off? Can we make a function that goes from B to D? so that we have a completed commutative diagram. Is there one that works? Let's see kind of what needs to happen. First, let's take something in B. And really what a function will do is take something in B and put it down to D, right? Let's see kind of a pathway we can do that. We have a function going this way, so we may as well just let's take a pre-image. So we have something in here. Now we have a function here. Let's just send that pre-image, which could be a subset, and down to something here. Then let's take the image of this subset. And if we get a singleton set over here, we're successful. If we have just one element here, we actually have a route from element here to here, which is induced by all these other functions here. And we actually will have a function that comes down. So, okay, let's take a look and see if that'll actually work in this particular case as we go. Okay, so original domain as follows. 1, 2. Okay, so notice that we have this split up a little bit more. So before we had like 1, 2, and 3, 4 together, and 7, 8 were together. What if we split up 3 and 4 and 7 and 8? Let's take a look. Is that what is in B? Let's see. Yeah. Let's see. B was 7 and 8 were 3 and 4 were split apart. So this is what B was in comparison. Okay. So we kind of split them up, but then so we've into another partition. But the end goal is our notice here in the final chunking, though, the final chunking has the same picture, kind of the same result as what we'd have for final outputs from inputs to outputs, as we would have otherwise. So this would work perfectly well if we defined the function, the last function, according to this pattern, meaning we send 7 and 8 to the red, 5 and 6 to the red, big red box over here, and so forth. This function would actually work just fine to complete that process out, complete the process, so that it actually would be the function that completes that picture. It's kind of an induced function in that diagram. Here, and let's see if there's anything else we needed to discuss here. Let me just kind of scroll up. Merge inducing principle. Okay. So given two merge functions, f and g, which share a common domain D, so they both kind of give a partition of D and chunk it up. We want to know, when do we have an induced function that goes from this place to this place? Let's see, if S itself is a collection of boxes. Okay, so hold on. Okay, so yeah, that's right. So this partition, so the partition that comes from this function here and goes back to D, if this partition that comes back actually fits nicely and neatly into the partition of F, then of course you can go this way and then forward. Because you can't go forward if you're split between two different boxes. You don't know where to send that, guys. So basically, if the partition that comes from G is a refinement of the partition that comes from F, then for sure we have a function that comes down this way. Okay, so kind of maybe we should visit that and look at that again. Notice that how, let's see about that. Okay, so yeah, okay, so 7, 8 and 5, 6, that's a partition of, yeah, so because the partition that comes from going this way, from this way right here, okay, so notice that goes from here to here is the red boxes, and notice that these are fit nicely into those red boxes. You're not split across the red boxes, so it's a subpartition. So of course, notice you may think, well, this looks a little bit different than that diagram up there because that was a triangle, that's a square. But see this F, it could really be extended like this from here to here if we wanted to, in some sense. So this F is generic; it doesn't have any relation to the F in the other diagram. So this right here would be like the full red boxes. So that composition, the full fibers, something here would be a whole red box. And so notice that that if we go back here along that way, we were completely in the red boxes. So we did get an induced function. Okay. Last but not least is skip patterns. All right. So any chunking defines a function and defines an equivalence relation. Why don't we take the integers? Let's chunk them as follows. Everything that has the same color will be in the same chunk. So -3, 0, 3, 6, 9, that's, and so forth. So all multiples of 3, let's let be a chunk. All right. And what about this? So 1 more than a multiple of 3. Let's let all those guys be another chunk, and 1 less than a multiple of 3 right here, or 2 more than a multiple of 3 are the same thing. Let those also be a chunk. This is an equivalence relation because it perfectly partitions the integers, this chunking process. We have a notation for this for this particular partition here. Z divided into 3z, so multiples of 3. Okay. So and in this particular case, we could use the notation 0 bar to represent one of the chunks, the chunk that has 0. That's multiples of 3. 1 bar, that actually represents the chunk that's 1 more than a multiple of 3. And 2 represents everything that's 2 more than multiple of 3. Perfectly partitions it out. Similarly, you could, okay, so you have this, similarly, Z mod, and we say this is Z mod 3Z is how we say it. 3 mods 3Z is the set. Now, if you're wondering kind of what this is going and what this is, actually, this is the crux for modular arithmetic, if you've ever seen that before, or clock math or whatever. Like, for instance, if you add anything in this set to something in this set, you actually get something in this set, like 1 plus 2 goes back to 0. Kind of a neat idea, which we'll be using later, but it's kind of nice to be able to think of this chunking in this chunking type of perspective, and we'll see more of that as we go along. Thanks for watching, and we'll end here for now.